Okay, good afternoon. Welcome to our lecture 7. So we are at the end of the fourth week. Wow, time flies. 4 weeks already. Good afternoon, everyone. Welcome back, and let's get started. It's 12:01, and yeah, it's Friday again. TGIF. I'm looking forward to the weekend. I'm sure many of you are as well. It's been a pretty tough week with exam 2, so hopefully it went more or less okay. But I'm curious at how you feel about exam 2 relative to exam 1. And this is our first poll for today, and it should already be open. Weekend is just starting for more exams. Yeah, that's very unfortunate. Well, still try to find some time to go outside and relax and enjoy the fall. It's really nice outside. Looks like a nice day today as well. One day closer to Fox exam. Yeah. Well, that should be too bad. I would hope. But all right. So let me scroll through the chat and see what we have so far. Someone was roasted by a TA mentor for using pen on the exam and writing the margins. You are allowed to use pens, so definitely there should be no issue with that. And yeah, writing in the margins and in between lines. Uh, it's okay as long as it is legible, and I can see what TA or mentor who tried to roast you was coming from, because they're the ones who will be reading your handwriting, and that sometimes based on exam 1 experience, sometimes it is extremely hard to read some people's handwriting, so they're trying just to make their job a little easier. And I'm sure if you write legibly, or if there's no room, ask for an extra sheet of paper, or use like on exam 2, the last sheet only had something printed on one page, and the other side of the sheet was just blank. So you could have used that to write whatever you couldn't fit elsewhere, and then just um, put a note in your main answer that please go to page 8 for something additional related to this answer. So that I think would work better, but definitely there are no penalties for using pens. And as always, we will do our best to read your handwriting. Okay, that was that. Okay, yeah, we'll see what people say about second exam. It was fewer questions. You cannot argue with that, right? It was just 3 questions. But regarding the difficulty, yeah. So for their, so someone said something funny. I think I saw it. Yeah, I got dumpstered by the hex dump question in exam. Yeah, I like the phrase. I of course feel sorry that you did, but hopefully other practice problem solution where you were asked to write that memdump function. Uh, um, hopefully that was helpful. Even if you didn't have time to write your own solution, at least hopefully you had time to look at our solution when it was posted. And I know it was, fairly, short time before the actual exam, but still. Okay, and yeah, looks like most people are finding uh, this exam 2 a little bit more, well, more difficult. So we. Oh, someone is saying that second exam was significantly easier. Uh, I don't know. Uh, is that the real thing, or people are just kidding? Yeah, December 8th, both Fox and Compwork. Ooh, not good timing. Will try to make Compwork exam easier, and on December 8th, for sure. And honestly, I was trying to make exam 2 easier because of everything that you told me about the career fair and all that stuff. And I thought it was okay, but apparently not. Well, yeah, that's the thing. Someone is saying that, yeah, all it means is if I get one wrong, I'm screwed. Well, yeah, but that makes a shorter exam. But then inevitably, the weight of each problem is much higher. All right, I don't think there's like a good way out of this, right? I can make longer exams with more problems. Each problem will be worth less, but then it will be longer. So all got hex dumped. Oh, bashed. So the last question. So I think we went over the last question. Well, you didn't know that it would be the last question on the exam, but we did go over this in the lecture, didn't we? So I made this script that was compiling and running the program, and that was essentially what became their question for their exam. Did you miss the lecture, or was it not helpful? Yeah, I'd like to know. Yeah, writing code feels weird. Not much we can do here, right? We need to see how students can code, and that's why we have to ask you to write code. And since we are back to in pen and paper exams, we don't have much of a choice. And yeah, like I was sharing with you before, I wish we could use a testing center where I could give you computers and compilers and pretty much everything except the internet. I would have absolutely no issues doing that. But that of course is not going to happen in this universe. Yeah, someone finished in like half an hour. Yeah. So yeah, one of the Ts told me that. All right. Yeah, let me scroll back. Panelists. All right. Yeah, Sage 3303. I know that there were some issues with that room, and again, Taze told me that it was very hot again. We are trying to find out if there's a way to control the ventilation or AC in that room. But I will share, of course, with you what we find out. But we're not gonna get another room. It is a little crowded, so we have to seat some people next to each other because we don't have enough enough seats in across two of our main rooms, DCC 330 and Sage 3303. And we tried to request another room, and we said no, that there are no other rooms. Period. So we have to struggle with these two rooms for the rest of the semester. Unfortunately, it's not something that I can do. And yeah, someone says exam felt fair, but was significantly harder. Well, it was kind of naturally harder because the material that we covered in there, for the second exam was harder. So if you recall exam one, it's just many questions just go directly from the syllabus or from course policies, and so exam two was more about their contents, about programming in C, and Unix shell, and all that stuff. Okay. All right. So let's. Yeah, I could be reading the chat and answering the questions forever, but let's get started. So panelists for today, we have 5 people, and if you notice, as we discussed last time, we opened up the sign-up sheet for even more people, but we will be as we did last lecture, we will be selecting a subset of those people. So if you didn't get an email from Cheyenne about being a panelist for today, it means that you were not selected for today, and then just if you signed up for other days, then just keep looking for those emails before each lecture. So for today, I have 5 people, and so can we can we check if all people who are supposed to be panelists for today um, are in here and are able to access Q&A?
Oh,
All right.
I'm a panelist. I think I have the Q&A here. I don't see any questions, but I think it's working.
Okay, cool. Yeah, so if you're a co-host, that means you're a panelist, and yeah, hopefully there will be questions in the Q&A. And actually, one of their questions was in the chat, which I think really should be in the Q&A, like about their sign-up link, right? So please, folks, post those questions in the Q&A, right? Because then it's gonna stick here. It's gonna be like pinned, and yeah, so test question, cool. So hopefully we have all 5 people here, Paul, Wyatt, Kekuyang, Mike, and Jack. I don't think, yeah, Jack is here. All right, so it looks like we have everyone. So let's get started with our agenda. So homework 2, submission page will open on Submini sometime over the weekend, and we will go over all the performance computation stuff today. So one thing I wanted to mention real brief is that in Zybooks, so those of you who are using Zybooks, I reorganized the material a little bit. It's still the same material, but I thought I can do a better job organizing it. So um, I split all the material by the week. And the upcoming week, week number 5, so the material is already here, so that you can you can start reading in advance if you have time over the weekend. You can just start by reading week number 5 material, uh, you know as the preparation for next week. So hopefully in this form it is easier to keep track of what exact content you need to read for each of the weeks. And I also made all their activities, participation activities, and challenge problems and Xi labs that are spread throughout their material. So I also split them into what are called assignments here. So you get points if you do them correctly. We cannot translate those points to real grades for our course because some people are not using Zybooks, and it wouldn't be fair to give people who did decide to go with Zybooks any kind of advantage, but I'm still kind of thinking I would like to recognize people who are doing this, additional preparation and additional practice on Zybooks. So if you have any ideas of any kind of recognition that we could give to those students, I'm willing to do that. But that recognition should not give any kind of material advantage. So we cannot give extra points towards the overall course grades, or we cannot give like extra lay days, because that wouldn't be unfair, with respect to students who are not on Zybooks. All right. So if you have any ideas, please let me know. Okay. Okay, first, yeah, someone is asking the first textbook problem. So yeah, let's do that. So let me go to our course materials. All right, did I? Yeah, so for Zybooks, I think I mentioned everything that I wanted, right? So activities are just participation activities. They're usually pretty easy questions, and you can reveal the correct answer if you want to. So those are easy. Challenge problems are somewhat more difficult problems. So after you've done those participation activities, you can try challenge problems. To see. Just to test your understanding further. And then Xylabs, you will not get any answers, but those are usually, it's like, a problem that you need like to write code for, or do something similar, and then submit. And so far it has been for C programming, but then later on it's going to be on MIPS that we will start talking about real soon, right? So Xylabs is really kind of your independent work, the way it's supposed to be, and you just follow the directions to write the code that directions are asking for, and then you kind of submit that code. It's going to be run by the auto grader on Zybooks side. It's actually Amazon AWS cloud service. That's what they use to run, all that code, and then this way pretty much if you got it right or not. So their solutions will not be disclosed, but you can test your own solution and definitely determine if it's correct or not, just based on what the output that it produces or the computation that it performs. All right, and then course materials. So homework 2, sure. Here's the PDF. And so textbook problems refer to our textbook, and I'm going to grab a paper textbook, just to make sure that we have their same numbering here in the physical textbook and on Zybooks, which I believe we should. So 1.5, for example, is the problem on page 60 of the physical textbook. And it says, consider 3 different processors, P1, P2, and P3, executing the same instruction set, and so forth. Oh, I need to probably share my screen. Yes, thank you for reminding me. All right, so yeah, I was talking about Zybooks. That's here. You can see how it's now broken into weeks, and all their assignments. All their assignments that we talked about, Zybooks assignments that are we cannot give points or any kind of official credit for in this class, but if you have any ideas of how we can recognize people who still do them, I'm open to that, right? So also broken down into weeks and 3 types: just activities, participation activities, challenge problems, and Xylabs. And for the problem, so 1.5, it's here. And I just quoted what that problem is from the physical textbook on page 60. And if we go to Zybooks, then the same Problems would be under exercises, so 415. I think I mentioned it in there. So the link to Zybooks is here, and oops, and Zybooks, right? And 1.5 is the same problem. Consider processes P1, P2, and P3, and so forth. So it looks like it's a match. Okay, it doesn't matter whether you're using a physical paper or non-interactive electronic textbook. It's there on page 60, and if you're using Zybooks, it's also here. So no matter what your choice was, you should have access to those textbook problems. And let me see if yeah, I am just every time I switch from sharing to not sharing or the other way around, I have to open their Q&A and chat boxes again because Webex would not remember them for some reason. So I'll have to organize my windows. Okay, so okay, so yeah, I think I answered that question or that request in the chat. But if I skipped anything or if I missed anything, please feel free to remind me. Right? Again, it's very difficult to keep track of things in the chat. Okay, and yeah, you don't need their textbook if you use Zybooks. So everything, Zybooks is a digital copy of the textbook. It's not one-to-one, so it's actually shorter. But everything that we want and we use in this class is in Zybooks. So if you got Zybooks, you got everything covered. Yep. And our panelists already answered that. Thank you, folks. Okay, so that is homework 2, and yeah, exam 1 grading done. Grade inquiries are open. So someone reported that there was a mistake in rubric for question 1 on one of the versions. So TAs are checking this, and if indeed it is found that there was a mistake in the rubric, then of course all students who were affected. Yeah, problem 1, I think. Yeah, so I think if I remember correctly, their answers to the last 2 subparts of problem 1 got swapped. So instead of false true, there was true false in the rubric, or the other way around. So TAs are checking for if that was indeed the case, and if it turns out that it was, then we will regrade all students who were affected. So no action is required on your part, and I will ask the TAs to make an announcement about that on the submittee forum. Right. If you notice any other problems, please file a grade inquiry. So you have 7 days, from when their grades were released, which was on Wednesday, I believe, Wednesday or Thursday. I think it was still Wednesday, yeah. So you have 7 days to file a grade inquiry. Okay, and so there are solutions to. So even if we didn't submit an inquiry, would they still check? Or, if after we verify that it was indeed a mistake in the rubric, then of course we will regrade everyone affected automatically. Okay, if it turns out that the rubric was correct and there was just a grading mistake on one student, then then that that or several students, then those students would need to file a grade inquiry, right? If the rubric was correct, we will not do automatic. We will not go over the entire class regrading them, right? Is that making sense? Okay, yeah, so yeah, you can file grid inquiries provided that you justify why you think you deserve more points. It's not going to be considered frivolous, so it would be fine. And for the last question on exam one, I think there were at least 7 errors, and we would get full credit to someone who identified 5 or more. So even if you didn't get all of them, if you got 5 out of 7, you would get full credit. But we would penalize for false positives. So if you said that oh, this is an error, but in fact it's not an error, then you would lose points for that. Is that making sense? Yeah, so and someone shared that yeah, so they already argued for their case, and they TA's got some points back or all points back, whatever the case might be. So yeah, exactly. TAs are humans, so they can also make mistakes when they're grading. So if you notice that, please be polite, but let them know that you think you deserve more points. It's a very natural process. So don't be afraid to file a grade inquiry if you think you deserve more points, and you can kind of justify why you think that that's the case. And if for some reason you're not happy with the grade inquiry process, you're requesting points, the TA refuses, and you just reach an impasse with them, feel free to escalate it to me if you still think you're correct. So, you can, if you're not happy with the resolution that their TA gave you, feel free to escalate it to me. I will look into that case for you. Okay. Of course, make sure that you genuinely believe you're correct, and not just because all right. Anyway, so that was that. Exam two, we are still kind of trying to push it to submittee. So we are still experiencing, largely the same issues that we had last time on exam one when submittee demons just failed to cooperate when after we upload a certain number of PDFs, and then Professor Cutler has to reset those demons manually, which of course is kind of slow. So hopefully they figure out what the problem is and fix it. But they were not able to do so in 2 weeks, so I don't know. So we should be done uploading hopefully today, and then we will actually start grading immediately. So as before, our target ETA for grades on exam two is a week from when the exam was given, and we will definitely try to make it happen. If it slips, hopefully it's only by a few days, not by the entire week, which was the case in exam one. So for exam one, it took us 2 weeks to get the grades back to you, and of course that's not desirable. So we definitely want to get the grades before their next before the following test. How do we know which test version we had? Look at the front page and count the number of funny characters. So I think in the first 2 exams they were diamonds, but they could be like spades or something similar. So look at their title page and count those characters, diamonds or whatever. Okay. And so that's exam two exam one solutions were posted. I don't think we have time to go over them in class, but if you look at them, they should be here. Okay, and yeah, you should be able to open it. Yeah, if you have a solution which is different from ours but equally correct, please feel free to share it on Submiti forum. I'd like to collect different solutions. I mean, substantially different, not just slightly different, but like if you used a totally different approach or different functions, fgets instead of fscan for something like that. So if your solution is interesting and it's significantly different from ours, and it's correct, feel free to share it on Submiti forum. That would be, I will just add all correct solutions to our, to this file, and of course, it's going to be beneficial to other students as well because they will see a variety of correct solutions, not just one correct solutions for many problems on exams, and it's true for future exams too. There will be more than one possible solution. There will be different ways of achieving the same thing. So we definitely want to see a variety of solutions, and yeah, so please feel free to send them our way. Yeah, review exam one solutions, and if you find any errors, any mistakes, anything that can be improved, please also share that with us. All right, and now we need to finish with our chapter 0, and then proceed full speed to chapter 1 because we definitely need to talk about performance. That's something that you will need to complete, to finish your homework. So to wrap up with chapter 1, so one problem that we haven't seen yet was the quoting, and that means so why do we need quotes? Well, because some characters have special meaning for the shell, like the star, which is expanded into, which is a pattern which gets expanded, so it's a wild card, or the question mark, or the brackets. I don't think we've seen brackets, but if you write shell scripts with conditionals like if else, then in certain cases you would use those brackets. Their space is also a special character because it separates commands. It separates command from the arguments and arguments, different arguments from each other. And if you want to use a space as a regular character, for example, you have an argument that is two words separated by a space. So in that case, you need to have that included, the entire argument included in double quotes, because otherwise Shell would consider it being, two different arguments separated by space, not a single argument that has a space in it. So double quotes. Right, we need double quotes. We shall see that there are other types of quotes that are used with shell, and they are different. We'll see them in a minute. All right, and the same applies, of course, to star. Like in this example, if you run this echo, it will treat star as a wildcard, and it will expand it to mean all files, with all names in the current working directory. What if we really want just a literal star? We would have to double quote it. Okay, and so then there are a few exceptions. So some special characters are not ignored, even if you enclose them in quotes. In particular, their $, which is the prefix for variable names. Remember, $, PWD, or $PATH path, and things like that. The double quote itself and the slash. Well, they're the backslash, to be more specific. So those would remain, would still be treated as special characters, even if they're within a double quote. So how do you include a double quote in a string that is enclosed by double quotes? Well, as this example shows, you just use backslash double quote. So that is called escaping. So you escape this double quote character so that it appears as a literal double quote in the output. And you can use single quotes just like double quotes, and then in this example, right? So nothing except the single quote itself is treated as a special character. All right, so it's somewhat similar to what we have in Python. So if you've taken if you've taken CS1, or if you happen to know Python otherwise, then you're familiar with this concept that double quotes and single quotes are pretty much interchangeable. And then we have backticks or back quotes, right? Which is that character. All right, it's not a single quote. It's a special character called a backtick, which is found on your keyboard. It's usually the upper left corner, roughly, of your keyboard directly below the escape key. So, and it's usually on the same key as the tilde. So this backtick, and it's a character by itself. Oh yeah, someone is giving us many backticks in the chat, so you can just copy those backticks. Yeah. Plenty of them, right? So backticks are special because in the shell, if you use backticks, it means you want to execute whatever is inside those backticks or back quotes, and and then basically replace their command in the backticks with the result of executing this command, as this example shows. Right? We do echo ls in backticks, ls is executed, and then the result is echoed. And PS1 is a special environment variable that corresponds to the shell prompt. If you do PS1 and then date is executed, and then the date is going to be used as the shell prompt. Yeah, well, all the syntax for Unix shell and all the special characters predates Markdown for I think many decades. All right, so all their basic syntax of shells and all the Unix commands, it's early 70s. Just to give you a historical perspective. So a long time before. I don't actually know how old Markdown is, but I don't think it's. I don't think it's 40 years old or 50 years old as Unix is. All right, so programming tools. We've used everything that we needed to write our source code, text editors, then compile. Debuggers, we briefly mentioned, didn't really go into much detail, GDB and stuff. And build tools, they are very convenient when we when we have more complicated programs or projects that contain more than one file, and then it's we have to solve the question, solve the problems like which order do we compile our code in, and what are the dependencies between different source code files, and maybe there are also external libraries for which we don't even have source code but just have a binary, and we have to make sure that that library is linked with our code when we want to produce the executable. And one example we already discussed it, was the -lm flag to link with the math library. But math library is a standard library, so that was easy. Imagine it's getting more complicated if the library is not a standard library, but a third-party library, or even if it's your own code, written for a different for another project. So things can get really complicated. And here, build tools are, come very handy. Did you folks use make in data structures? Was it introduced in data structures? No. Oh, wow. Okay. Well, when we get to writing more complicated code, remind me to tell you and give you a few examples of using, writing make files and running make. It's a time saver. It's very convenient. It's very powerful. It will save you a lot of time. So just please remind me. And yeah, someone used it in their IDE. Yeah, but you should be able to use it from the command line. It's really not that difficult. At least baseline makefile syntax is pretty straightforward. And yeah, but we'll talk about it. Just remind me when we get to writing C code, for MIPS with multiple C files, and then kind of compiling them together as one project. Okay, and then. So std in, std out, std error, we talked about them. So they are special files. So they have file descriptors or file handles, which in your C code are represented by file pointers or file star. And you don't need to open those files, so you get them, for free in your program. They are already open. You get those descriptors when your program is run, and those have fixed values. Remember, we were redirecting 1 and 2, so 1 std out, 2 std error, and for anything that is not one of those 3 standard files, or for all the user files, we have to do file I/O operations. At a minimum, we need to open the file and close the file, hence fopen and fclose. And then once we have this file, open, we can do something with it. We can do fprintf, fscanf. So names are pretty self-explanatory. They are exactly as regular printf, regular scanf, except for they take an extra argument, their file star pointer, right? So the file handle or the file descriptor, and then they will perform this action with a file. So print to the file, scan from the file, and so forth. And so here are a few examples. Open the file, you call fopen. It returns you that file star thing. And you need to analyze that return value, because if it's null, it means that the file was actually not opened successfully. And of course, you want to know this. Their first argument of open is their file name itself. It may include the path, of course. It just, as you can see, it's just a C string. And then the second argument is their mode. It specifies what you plan to do with the file. So how you want to open this file, what you want to open this file for. So W stands for writing. So you create this file. If the file already exists, it will be deleted, and a new file will be created with this name, right? So effectively, it's truncating the file if it already exists. W plus means that it is for reading and writing, and R, reading, just for reading. Any attempts to write into the file would fail. And R plus is for reading and writing. The difference from W plus is that if the file already exists, it will not be truncated. It will be just open. And if the first operation you do on that file after you open it is writing, then it will be effectively adding adding contents to the existing file. There's also an A mode, which is not listed here. A stands for append. This is specifically if you want to append to the end of the file. Yeah, truncate means reduce, get rid of the stuff. All right. So if you truncate the file, you get rid of everything, all the contents of the file, but you keep the file, and it's going to have a 0 length. And of course, truncating, for numbers means just get rid of the of everything after the decimal point. All right, fclose, you are expected to close all files after you're done with them. That frees up the resources that the operating system uses to support your I/O operations. And it is especially important if you're writing to the file. So if you only read from a file and you forget to call fclose, it's nothing bad is probably going to happen. So not because you were not modifying the file. But if you were writing to the file, so any of the modes that support writing, W, W+, R+, A, if you do not close the file, you may actually not see the last batch of stuff that you wrote to the file physically in the file, because there are buffers in the operating system, and if your program ends without without closing the file properly, those buffers may actually never be dumped into the actual file. So to put the long story short, make sure that you close the it's a good habit. It's a good habit to close all the files that you opened, right? But at the minimum, you should close all the files into which you were writing. And fscanf, very similar to scanf, just regular scanf, but it gets the data from the file, not SD in. Other than that, it's exactly the same. So here we are, if we look at this example, we open the file, myfile.txt, for reading, and then we read. And if my file gets the file pointer that fopen returns, and we need that my file because every other operation with a file will, with that file would require us to specify the file descriptor or file handle, which would be my file. So we need that my file. And if it turns out that it's null after the assignment of whatever fopen returns, then it means that fopen failed. It could not open the file. Most common reason, the file doesn't exist where we told fopen it should be, or maybe the mode of the file is such that we do not have a permission. So, for example, you're trying to write to the file, which is read-only, or you don't have a write permission. And as you remember from our prior conversation about access permissions to files on Unix, the read permission is a separate permission, so you can actually set the permissions such that someone would be able to write to a file but not read from the file. Okay? So in this case, even trying to open the file for reading would fail, but if they try to open the file for writing, it would succeed. So if my file is not null, we can go on and try to read from that file and interpret whatever we read according to the scanf format string, and then have fscanf put the corresponding values into I, j, k, and buffer, and then we close the file. So does it go by line or all at once? fscanf will just try to complete the job. So it will try to get the first value, which would be their integer. So it will scan the file for characters until it encounters a white space character, and it will try to convert everything that it captured into an integer, and then it will skip the white space and try to, and then keep capturing the characters for the second D value, for the second integer value, and so forth. All right, so that's fscanf. So if you run fscanf twice, will it start from the next piece of data or from the beginning? It will start from the next piece of data, right? So in the file, there is this invisible, but you can actually make it visible, right? There this current position. So you open the file, you read from it, and next time you read, if you didn't close the file, right? If you just keep calling fscanf or fgets or any other similar function, you will keep reading from from the position where you left this file last time you read. Okay, so it will maintain this internal reading position that as you read would just move through the file. Okay, and so that's fscanf, and scanf is similar to scanf, but it reads not from the std in, but from the string, from their array of characters, and hence the additional argument here for buffer. And I think we've seen scanf before in early examples, so hopefully you're familiar with it. So here, note that we are opening this file, myfile.txt, for writing, and then we read from that file into the buffer. You see how we call fgets to read the entire line. We assume that the file is a text file, because if we were to open a file, a binary file, or if we wanted to open the file as binary, we would append character B to the mode. So it would be like WB. Since we don't have this B here, it's just W. It means it's a text file. And so we read from that file one entire line because it's a text file. So there is a notion of a line into the buffer, and then we ask this scanf to read from the buffer and convert the values into 3 integers and 1 string, and then we close the file. All right, and finally, fprint, again, no surprises here, works the same way as printf, but with printing not to the standard out, but to the specified file. Of course, file needs to be open, and here we have an example of using W+. And with this example, we have our next poll related to this example. So please take a moment to answer our poll number 2. And one thing let me digress a little. So one thing that we implemented finally in Rainbow Grades. If you look at your Rainbow Grades, if you earned an additional lay days, and some people have, there were like 20 or 25 people who earned an additional lay day. So those people would see here down below a note that they now have 4 lay days for the entire semester, starting from, I think, September 21st. Right, so that's the effect of those polls. So it's real. So some people can already enjoy 1 extra late day, and of course we will continue doing this, unless unless you folks decide it's no longer attractive, and we should not do that. All right, and while we are here at the polls, let's look at the results of our polls from last lecture. We do that usually. So here, what do you need to do? Type jobs and press enter. That's the Vox Populi, and I actually, in this case, happen to disagree, because look at the last command here, sleepy35. There's no ampersand at the end, which means that the last command that you run is just going to be in interactive mode. So the std in will be associated with this last command. So whatever you type will go into the sleepy, and it's not expecting any input, so it's just not going to be it's just not going to do anything to you if you just type jobs and press enter. So I believe so this second most popular option is the right answer, right? Because here you need to press Control Z, which would send Sleepy in the background and put it into the stopped mode. So it will no longer execute. It will still be a job, but it will be like paused, and but that would bring you back to the command prompt, and there you could type jobs, and then if you would be willing to, make your last job execute again, you would do something like BG3, and that would restart. That would allow Sleepy 35 to continue. Okay, yeah, and yeah, BG list. It's just a filler. I don't think it's a real thing. I don't think BG would take a dash list. And PS is to list the processes, and every job is a process, but not every process is a job, right? So you if you want to look at all their jobs and their status, you have to run jobs command. PS would list all the processes, including those that are running as part of jobs, but it would not tell you anything about the status of the job. And what was our number 2? Oh, that was just their your wish list for exam 2. So yeah, pointers and dynamic memory allocation, that was entirely question 2, right? With arrays and pointers, and question number 1 as well, right? Dynamic memory allocation was a big thing because that's heap, right? And pointers. So hopefully I followed what I promised I would about giving more problems according to what students voted for. And yeah, so there was nothing on jobs in their exam again because very few people wanted to see those problems on their exam. All right. Yeah. Poll number 2 was just a survey, so you would get full credit no matter what you answered. Okay. So that's that, and yeah. So I just opened that pop quiz, and so pipes are also implemented as file descriptors or file handlers in Unix, and so there's a method called popen in the standard C library libc, and yeah, you will get a lot of practice with this popen in operating systems. So if you recall their practice solutions, the practice problem solutions, then there was one where we ask you to write a shell, like a simple shell. And we will talk about their fork and exec in just a minute. And you will do a lot more fancy stuff in operating systems class, where you would be writing your own shell with support for redirection and pipes and all that business. So it's just to whet your interest in what is ahead of you in operating systems, so that you get some early exposure to this idea. We can run our own shell, right, and make it better than any existing shell, bash, fish, or anything, or zh or anything like that. All right, so that's pipes, and finally, this part, that there are like a dozen of slides or so. It's like a gentle introduction into operating systems. So basically, it summarizes what many of the things that we've already discussed and seen. So there are resources, hardware, like our I/O devices, memory, that operating system needs to manage and control who accesses those resources, and making sure that different software access these resources in a fair manner. And particularly about processes, we mentioned that a process is a program running, and we can of course have the same program running at the same time as multiple times. We had an example with jobs where we would run the same sleepy program multiple times. So it's the same program, but it can be every time we launch it, it's its own separate process as far as the operating system is concerned. So operating system is responsible for the whole support of running the programs, creating the processes, making sure that they can run, making sure that they can that they are allocated CPU time. If we have a competition for the CPU time, which is usually the case, usually we have a lot more processes than we have CPUs. And when the process is done, it needs to be terminated, and all the internal data structures that were associated with, keeping track and managing that process needs to be freed. Processes also usually need, or quite often processes need to communicate with each other. So IPC, inter-process communication, is another service that operating system provides. And multitasking, we already mentioned, right? We have more processes than processors than CPUs, and the operating system needs to decide how to schedule processes for execution to give that illusion of parallel execution of many processes. Okay, it doesn't look like kill is the right command. I think we tried the kill with both the processes and jobs last time, and I think it worked. But please feel free to follow up and ask more questions if something is not working out for you. All right, and POSIX is standard for operating system interface. I'm not going to talk too much about it, but it's a standard, and the majority of Unix, Linux operating systems are actually do implement this standard. Not all of them implement it completely, or quite often there is a mode that you can turn on, which kind of ensures 100% POSIX compatibility and no other extensions. And you can turn it off if you want, some extensions which are not POSIX compliant. So in any case, it's a very important standard, for operating system design, because many operating systems support it. Okay, so that's the standard, and so system calls is a way of a user program to request some service from the operating system. So it's basically a function that you call, but that function will be implemented by the operating system, and it may be operating system specific. For example, fork is something that we will just talk about it, and if you write a C program calling this fork function, it would work on a Unix Linux system, but not on Windows. On Windows, there are other ways to, similar in a sense, but it would be a different function. So why is this connection between C and Unix? Well, as you probably know from history, Unix was originally written largely in C. Well, parts of it were written in assembly, but the other major language that was used for early Unix implementations, and Linux to that matter as well, was C, and therefore there's this inherent kind of connection relationship, relation between Unix and C. All right, so Unix processes, we have already seen them from PS command output. So each process has a PID or process ID, user ID. That's their user who started their process. Same for group ID, right? And remember, user ID is linked to username, but user ID is a number, whereas username is typically a string, like Kuzmik or something like that. Current working directory, memory that is used to hold their at least their image of their binary program that this process executes, and a bunch of other stuff. So in Unix operating systems, the only way to create a new process is to issue the fork. It's a system call. So from the standpoint of a C program, it's just a function. So when you call this function, it splits the current process into two processes. So their original process remains, and it's called a parent, and then the new process that got forked from the parent is called a child. And how does the code know which process is a parent, which process is a child? The answer is it knows that from the return value of fork. So fork returns the value which is different for the parent and the child. So the child process gets their 0 return value from fork. The parent process gets their process ID of the child, and that's how they know the difference. When after fork was executed, their child process receives a copy of the parent process. So it continues to execute the same program. It inherits the same binary image of the program it executes. All the arguments, everything the same. But of course, it's a new process child, and it gets a new process ID. So that means that a child, to be useful, certainly needs to change the program that it executes. Otherwise, it's just going to execute the same program that the parent was executing, and it's not going to be hugely useful. And for that, there is another function, or even a family of functions, called exec, right? Exec and the friends. So we will talk about them in a minute. All right, so before that, child inherits almost all attributes from the parent, including current working directory, user ID, group ID. One thing that it does not inherit is the process ID. Each process in the system in Unix has a unique ID, so we cannot have two processes with the same ID. That's that's something operating system is enforcing. And there is this fork system call that we just talked about. It's if you want to call any system functions in C, you need to include this header uni stdh, and that's their synopsis for the fork. It doesn't take any arguments, and it returns their PID, process ID, which for their child is going to be 0, but for the parent, it's going to be the process ID of their child that was spawned from that parent. So that kind of means that fork returns twice, once for their parent and once for the child, because remember, from the moment fork is called, we now have two processes. Okay. Here's an example. It's also in their examples under lecture notes. So we can tell if we are in the parent or in the child after fork is executed by, just looking at the return value of fork. If the return value of fork is not null, not 0, it means that we are in the parent, and that non-zero return value from fork is the PID of their child. Otherwise, if fork returns 0, that means it's a child. All right, so that's their code example, and this is a well-known thing called a fork bomb. All right, because it is really going to bomb your computer if you try to run it. So don't tell us we didn't warn you. We did warn you, right? So why is it dangerous? Why is it a bad example? Well, why is it a bomb? Because we call fork in a loop. So imagine what's going to happen. We call fork, and to their uh, parent, it will return non-zero. So it will execute the body and print I am the parent off. And then there will be the next iteration of the loop, and it will call fork again, return non-zero, and another iteration, and so forth. So it will be an infinite loop here, only for the parent. For the child, fork returns non-zero, which means that we print that message and we immediately exit the loop because fork returned 0, which is interpreted as false for the purposes of the while loop condition. All right, yeah, and if you did run this fork bomb, try pressing Control C and stop the program. It might be too late, but it might work. All right, yeah, and don't do this on any of campus machines, please, or make sure they don't catch you. All right, so as we mentioned, fork creates a new process but keeps their child process executing the same program. So it's not particularly useful by itself, but of course it's needed because that's the only way to create a new process. But after we created this child process, we want to call one of exec methods to actually change the program that a process is running. And actually you can use exec even without fork, right? So for example, your program runs and then at some point it decides that it wants to execute a different program. It can do so by calling exec. And as I mentioned, there's a family of exec functions, and I believe all of them are listed here. The difference is whether their environment array, the array that contains all environment variable, is passed into or not. So if it has E in the end, it means that environment variables, the array with environment variables is passed into. And other differences are basically just how their command line arguments are passed, whether it's just a list of command line arguments or it's they are packed into the array. So please review manual for those functions to see what they differ in. The difference are really minor, as this slide suggests. All right, so when you call exec, it changes the program that the process is running. So as one of the arguments, you have to specify which program you want this process to now run as the result of calling exec. And if that program is found, and if changing the program that the process is running is successful, exec will never return. So this is a very important point, right? You may actually see that exec never returns, and because if it does return, it means that something something did go wrong. So if exec doesn't return, it just means that the process now runs a new program from the very beginning. And so here's an example. All right, so here's a synopsis for exec-l, takes a path and a list of command line arguments for the command that we are about to switch this process to. So we say that when if this line appears in our code, it means that we want our code to switch the program this process is running from whatever it was running before to reverse. We assume that it's a command, so it's an executable that can be run as a command, as a program, and we pass in what will become command line arguments for that new program. So first argument by convention is the name of the program itself. That's why we say reverse here as arg0, and then hello as arg1, and null means we don't have any other arguments. So just two arguments, arg0, arg1, and our process will start executing the reverse, and this reverse will have two command line arguments, reverse and hello. All right, and here is a complete exec-l example where we are actually switching our program from running the code that it was running before to running ls. And a note that this printf, last printf, normally would never be executed. If we switch the program that this process is running, we will never have a chance to execute this printf because exec-l or any exec function changes the program from this program to ls. And of course, ls will not have this printf line that we have here. So this is basically dead code, unreachable code, which is very non-obvious, but that's really what it is. And note how we called exec, one of exec functions without fork. So fork and exec very commonly go together hand in hand, but you can use exec without fork, you can use fork without exec, as these examples demonstrate. And here we have ls as the first argument and -al as the second argument. So we are asking ls to execute. All right, so as we mentioned, fork and exec all often go together. Fork makes a new child process, and then their child switches the program from the program that it inherited from the parent process to whatever the program it really wants to execute. All right, so here is the here is the exec and fork example, which is also in lecture notes, so you can actually run it. Okay, and yeah, we see that this is the method for that called child. The child will call, and this is the method that the parent will call. So this wait call here is important because it allows the parent to wait until the child is done. So this stat is something that we get from. So let me. And I think the code isn't in the lecture notes. Let me see. I think I. Yes, it should be there. Thank you. Yeah, it's probably one of the previous lectures because we were supposed to cover this, I think, a lecture or two ago. So all the examples would be there. All right. So now, yeah, and just bear with me for a second. Lecture notes. As you can fork, it's right here, and I wanna open it. So that we have, yeah, it's not very convenient to look at their code on multiple slides. So here is the full code in one screen, and I can zoom in to make sure we can see it better. All right, so yeah, so I wanted to talk about this stat thing. All right, so a stat is their variable that will be set by their by wait. All right, it will basically indicate the PID of their child that finished. Okay, so that's why we have an ampersand stat. And yeah, so we fork, we get their PID of that fork returns. If it's not 0, we are in parent, and we print f, and we call parent, which basically all it does, it is waiting for the child to be done. Why is it needed? What happens if the if our program calls fork, and then the child will take a longer time to execute, and our parent process is done. It has no other code to run, and it just reaches the end of its main and returns or calls exit while the child is still running. That would make the child what is known as a zombie, right? Because this child was linked to this parent, right? This child is the child of the parent, but the parent is no longer living, and that leaves, that makes the child feel very lonely, so that the child becomes a zombie. Okay, and or an orphan, yeah. So and for that reason, it's best to be avoided, because a zombie process, it will stick around in their operating system even once this process is done. It will occupy their process ID, and depending on the operating system, it may clear out all the zombies, but not operating systems do that. And it's not taking up a whole lot of resources, but it still would occupy some resources in the operating system, and at least it will hold on to its process ID. So yeah, Unix systems are funny if you think about the terminology, right? So we have zombies, and we have demons, right? We just talked about demons when we discussed submit issues. So it's like older scary creatures, demons and zombies and whatnot. So yeah, that's the importance of this wait, call to wait. All right, we want their parent to not terminate before all the children that this parent spawned are done. Okay, and because like I said, the operating system will not automatically kill the children when the parent exits. All right, the children will become zombies, but they will stick around, and of course the parent will be gone. Yeah, it's getting close to October 31st, the Halloween. Yeah, spooky season is near us. All right, so that's that example, and yeah, we don't have time to go over this in detail, but look at their practice exam solutions, right? So that were posted for exam 2, right? So this is their code for a very simple shell that it's simple, but it uses a custom shell prompt, so that it prints their host name, the username, and the current dated time, I believe, and not the daytime, the working directory, right? I think that's the prompt. Oh no, it does print the dated time. So username, host name, machine name, date time, and the working directory. So it's a little fancier than your standard default shell prompt. Of course, you can set the shell prompt with for your shell anything you want, and we've seen an example like doing PS1, changing that variable. But this is another way to do this, for your own custom shell. And then this shell takes commands from the user until it sees the command, a special command exit. When it exits, and if it's not exit, then it executes the command. And executing the commands, executing a command means that we have to spawn a new process. So we fork, and then in the child we change their executable image, the program that the child is running, to whatever was requested by the user in the command, and then we wait until that child is done. Will child run automatically after parent run? Yes. So when you call fork, it kind of creates a copy of the parent process, and then two processes execute the same program, you know, but they are separate processes, so they may take different paths through their through their execution, and they will take, if you have this if here, right, immediately the parent will execute the different code from the child, because the parent will execute this, the parent will execute this part, and the child will execute this part if their PID returned by fork is 0, and the parent will execute this part. So it's the same code, but it doesn't mean that both processes, the parent and the child, will execute the exact same thing, because they may take different paths through the same program. Is that making sense? For the stat, don't really for the stat have it. It's come on. Yeah, it's here. Yeah, it's just the status that we are not even using here. Quite often in code examples, you would see that wait is called with null. Yeah, let's not go into that. It's not hugely important, given the level of exposure that we need to get here. Okay, and why would you have to create a child? Well, you create a child because that's the only way to create a process in Unix operating systems. And of course, you may ask, it's a chicken and egg problem, right? So if the only way is to call fork, well, fork has to be called from some running process. So who creates that first ultimate, initial process that would be the parent of everything else, right? Yeah, the first process in a process with ID 0, the init is created separately, differently, right? We have to make this exception, otherwise we would have this chicken and egg problem. But then wouldn't there be two of the same processes with parent and child? Yes, exactly, there will be. They will be, they will not be identical. They will be two different processes that just execute the same program, but we can change the program that any process executes with the exec function. Okay, yeah, so the init process is the ultimate parent of all other processes, right? Because initially on day 1, only that process exists, and then all the other processes are spawned as as children, grandchildren, and so forth from that init process, the first ultimate forefather of all the processes. All right. So the same program could interpret different data, of course. The fact that you run the same program, imagine you run the same program, but it doesn't mean that their statements that these programs execute are exactly the same, because you have your ifs, your loops, and whatnot. So the path through the same program may be different, right? It's the same code, but how it is executed depends on the environment, on what the user entered, on what your tests in if conditions are. So the same binary code will be executed differently depending on which paths you take through the program, and this is exactly what we see here. So before this command, before this fork is called, there is only one process. Once you call fork, when fork returns, you now have two processes. but the return value of fork to each of those processes will be different. Fork returns the PID, so non-zero value to their parent and 0 to the child. And since we have this if here, immediately, well, this if here, right? So this if is just to see if the fork was successful, because it may not be, right? But this if is making sure that even though the parent and the child execute the same program, they take different paths through the program and they execute different statements. Because so if PID is 0, it means it's a child process and it will execute this block. Otherwise, if PID is non-zero, it means it's a parent. The parent will execute this piece. All right. So they will execute the same program, but different statements, because they will take different paths through through the program after the fork, because we made this distinction, right, which allows us to distinguish between the parent and the child. All right, so that was that, and so that's just this example, and the output. So I'm going to run it. It should be pretty straightforward. We discussed, I think, all of it. And here is the pop quiz related to this. So let me actually open that last pop quiz for today. So we have 3 today, and here you go. Okay, and then we have about 20 minutes left. So we definitely need to talk about performance. So let me actually, skip some of the history stuff. It's important, and we will go back to it next time, right? About the history of computing, the components of a computer. It's not hard material, and we can certainly kind of swap the order and do it a little later. For now, it's important to concentrate on performance. And so let's start with this slide to make sure that we cover this material today. So if if I show you this data, and so those slides are now, so we are starting, the material that we are starting talking about right now is from our computer organization and design book. So you will see all those pictures and whatnot in your textbook, or in Zybooks, of course, as well. Okay, so if you want to refer to that. So if I show you this data and ask you which airplane has the best performance, what would you say? Airbus 330, because my dad flies. Wow, that's amazing. Yeah. So yeah, I can definitely take that as an answer. Yeah, Concorde. Yeah, that was a big thing in their history of aviation. But the right thing to say is exactly define performance, because what do we mean by performance, right? Do we mean that we want to fly a single passenger, from point A to point B in the least amount of time? That's one thing, right? So if that's how we define performance, who would be the winner? If we just care about moving one passenger from point A to point B in the least amount of time, what would be the best choice? Yeah, Concorde, exactly, because it is the fastest, right? If we have one passenger to move from New York to London, you can't beat Concorde, even to this day, right? And of course, Concordes are no longer in operation, but still, and that's one definition of performance, right? So yeah, BA, I guess BAC, I guess it stands for British Airlines Concorde. That would be my guess. All right. As you can see, from other plots, the passenger capacity of Concorde is their smallest across all their vehicles, all their planes that we have, here that we're considering. So if you need to move, let's say 500 people, then yeah, it would take you, 3 trips by Concorde, right? So clearly, Concorde would no longer be the fastest if you're measuring performance as the amount of time to move 500 people between New York and London. And then you look at their passenger capacity, and you would be, oh yeah, Airbus 380 is really the winner here, right? Because it can take 800 plus passengers, and yes, it is slower than Concorde by a lot, but it takes 4+ times the number of passengers. All right, so. And this we can express with this, with this new metric that we call passenger throughput, which is passengers times miles per hour, right? And then, that basically just demonstrates that we can have different ideas of what the performance is, right? Because, for example, if we need to move, if points A and B are more than 9,000 miles apart, then it would take us 2 trips of Airbus, as compared to just 1 trip by Boeing 777, right? Because it has a quite noticeably longer range, yeah, but their passenger capacity is also much smaller, right? The passenger capacity of Boeing 777 is what, roughly 3 times less than that of A380. So that means that probably Airbus would still have the best overall throughput, even if we consider that it might potentially need to make multiple trips. All right, and again, it depends on the number of passengers, right? If we're talking about carrying exactly like 250 passengers, then you won't be, across 9,000 miles, you wouldn't be able to beat 777, okay? Because it would just take 1 trip, whereas for Airbus it would take 2 trips because its range is not sufficient. All right, so that's the idea about the performance. We have to make sure we agree on, what performance we are talking about. And a few important metrics that we are concerned and now we are talking, we're getting closer to the discussion of how this relates to the topic of the scores. There computers and programs and commands and instructions. So the response time we define as the amount of time it takes to perform a certain job, and throughput is the total work done per unit of time. So it's like operations per second, operations per hour, transactions per hour, something like that. And these are 2 different metrics, right? So both are important, but we have to agree which one we mean when we say the highest performance. In many contexts, though, throughput makes a lot more sense to use as a performance metric than just the response time, right? So, if I tell you that this program can execute can run complete the task in 10 seconds, but then it wouldn't be able to complete the next task in the next hour, then yeah, response time is good, but throughput would be abysmal, right? Because it has this long waiting time after completing the job, it would have to wait until it is ready to run again. So throughput in many contexts is a more meaningful metric to use. All right, we need to focus, let's first focus on the response time and then talk about throughput. And both response time and throughput are affected by their by the characteristics of the hardware and the software, including like operating system, the processor, the memory, and so forth. Let's start with some simple examples, and let's see if we can possibly replace the processor with a faster processor or add more processors, and how that might affect the response time. Here's the first formula, very straightforward. If we define performance as just 1 over execution time, very simple. So if we have a program that takes 10 seconds on processor A and 15 seconds on processor B, we can compare execution times. So they are different by a factor of 1.5. So A is 1.5 times faster than B. So the formula is pretty straightforward, right? So we compute the performance just as the ratio of execution time. And so we call this relative performance. So how do we measure the execution time? There are different approaches to that as well. So we can only count their CPU time, so their amount of time the processor, the central processor, was occupied with the task, or we can also include their operating system overhead, the I/O, which is typically slow, or idle time when the process was just waiting for something, not able to proceed. So we have to agree on how we measure time, what we account into their total response time. And CPU time is usually a very important component of the elapsed time, because in many cases it actually dominates. All right, so it dominates the overall running time. Although I/O, because it tends to be slow, so if the program is very I/O intensive, I/O time can actually be much larger than CPU time. So from this, we can kind of see that there are problems that are I/O bound, or that are very I/O intensive, like reading, writing files, but doing almost no computation. That would be an I/O bound problem, versus some compute intensive programs, like doing your I don't know, pi computation, with some crazy number of digits after their decimal point, right? Almost no I/O, nothing, no files to read or write, most likely, but a lot of CPU usage. Yeah, crypto mining. Yeah, that's another one, right? Very compute intensive. Here we go with all our GPUs. All right. CPU time is the time spent executing instructions, executing commands of a given job. So excluding I/O time, excluding the fact that the CPU might be switched between different jobs and so forth. All right. So all CPUs, all modern CPUs, and actually all digital electronic these days is clocked, and we will talk more about why it is a requirement. A very easy explanation is because it allows different components of the system to work in synchrony with each other, and that synchrony, right? It's like a heartbeat, right? It is established by their master clock, and usually in complicated digital systems like a modern computer, there would be multiple clocks. So memory might be clocked differently from the CPU, and there's an FSB front side bus clock, and it's complicated. But all in all, clocking is what allows different parts of the system to kind of work together, and know when to do what by just observing this clock. So clock is really just this pulse waveform that oscillates between low voltage and high voltage, and that determines their speed of all their operations that all components of their computer system perform. Okay, so we can see that in this diagram, right? So we have the clock, and so their clock is periodic. So we can talk about the clock period, right? The period is from this rising edge to the next rising edge of our pulse, of our um, pulse width waveform. And then all actions happen within the clock period. So for example, reading one, byte of data from memory and transferring it may happen within one clock cycle. Even if it takes less than one clock cycle, it doesn't matter. Next action would not happen until the next clock cycle. It is possible that certain actions take multiple clock cycles, but it would be again an integer multiple of clock cycles. So all updates happen only on their boundaries of the clock, and most typical at the rising or falling edge. So here you see the update state happens on the rising edge. It is also possible in more advanced systems to something happen on the falling edge, like halfway through the clock period. And we will get into the details of that when we talk about gates and all their internal hardware. So it's coming up. I do not mean to scare you, but it's coming up. So please uh, you know, uh, be ready for that. But for now, there are just a couple important formulas that we need to remember. First is the clock period. So this is just their it's a time unit, so it's in seconds, or fractions of a second, of course. So it's just the length of one clock period. And if we take the inverse, that would make the frequency. So hopefully, this is something that you remember from your physics, right? So that's the frequency, and it is in hertz, or kilohertz, or megahertz, or gigahertz, right? So those are units of frequency, and frequency and period are just the inverse of each other. And if we want to compute their CPU time, then we just take their number of clock cycles and divide it by the clock rate, right? So if we know that a certain program takes 10 cycles, 10 CPU cycles to complete, and we want to convert it to time, we just multiply clock cycles by clock cycle, clock period, or we divide clock cycles by the clock rate. And clearly, we can improve the performance if we reduce the number of clock cycles, or if we increase the clock rate, or or both, right? So that's the job of a hardware designer, to find the trade-off, because things are not easy. Things are mutually dependent, right? Usually, you cannot just reduce the number of clock cycles and not pay for that with the degradation of some other uh, characteristic of your CPU. So it's always a trade-off. So here's an example. We have two computers, A and B. Computer A has a 2 gigahertz clock, and for a certain program, it takes 10 seconds of CPU time to run it. So our job is to design computer B so that the time is reduced from 10 seconds to 6 seconds for the same job, for the same program. So we know that we can do faster clock, but we would have to pay for faster clock with more cycles, right? So, and here's the ratio: 1.2 20% more clock cycles if we go with a faster clock. So how fast should we do? Should we make our computer B to meet the requirement that the program runs in 6 seconds? So clock cycles divided by CPU time, this is the clock rate of B that we need to accomplish. And of course, this is something that we need to find. So we first find the clock cycles of A. So we just multiply 10 seconds times the frequency. So that's the number of clock cycles that our program takes, 20 billion. And then we know that for computer B, we're going to increase it by 20%. And then we should achieve their 6-second running time. So that's their CPU time here. And from this formula, we see that we have to go with a 4 gigahertz clock rate for for our computer B. So the interesting thing to note here is that if we compare A and B, we increase the clock of computer B by a factor of 2. So it might be tempting to say that oh, we will be expecting all programs run in half the time. But in fact, we don't see that. We see that their running time went down, but not by a factor of 2. It went from 10 to just 6. And this is because we had to pay 20% more clock cycles for our increased clock rate. All right, so it's 1:50, and we are out of time, and we didn't go through all the examples that I wanted related to performance, and because of that, what I'm proposing is actually move the deadline for our homework to by a few days, so that we can get more practice with performance computations on Tuesday, and then how about having homework 2 due on Thursday without late days? It's just going to be moving the deadline. Would that be good? Okay, cool. So I will make an announcement for people who are not here today, and then I will adjust their dates on submitting. But still, I will make their submitting page open for submissions over the weekend. So if someone is ahead of the schedule, you can you can submit. All right. Thank you, folks. Yeah, I'm getting great responses. Thank you so much. So we are done for today. See you on Tuesday. Have a great day. Enjoy your weekend. Get some rest. Forget about Fox exams. For a day, and just enjoy nice weather outside. All right. Thank you so much. Talk to you later.